How you doing? This is Mike here again, and we are going to continue on with our discussion on trigonometric functions. And I know I guess I maybe should have labeled the last video a little bit different than trig functions, but we really didn't discuss any functions. But I'll be leading into it in this video. So I noticed in my last video that I wasn't explicit when I used some terminology. So I want to be a little bit more explicit in this one. When we often discuss angles, we usually do so in relation to two rays. And I know I said legs before, and I should have probably stated something a little bit better. But here we will call this the initial ray. So I'm going to call this the initial rays. And rays, they extend infinitely long. They do not end. So they have one endpoint. They have one endpoint, and that endpoint will exist there at the origin. And this will be the initial ray. So this will be in the initial ray, and this here will have another ray. We'll have another ray, and this we're going to call the terminal ray. The terminal ray. And in between these two rays, we're going to be able to relate the angle that exists between them. And the most conventional sign that we discuss is usually the angle theta, but you often can see several different other Greek symbols that are used. Often you could see theta, you could see phi, you could see delta, but the most conventional one is theta. You might see an alpha or a beta too. So, well, not beta, you might see beta as well, not a beta 2. You'll see that in biochemistry, but at this point we'll see thetas. But remember, when we discuss the terminal ray has a very important nature in the fact that specifically in regard to the angle theta that's created, if this right here is our initial ray that starts at the x-axis, we could have an angle that not only goes around our axis once, that goes around and comes back to the axis once, but it might go around twice. So it comes back around again. So the angle would consistently get larger and larger. So if I can make maybe I don't know if I can do this with the technology, but imagine if I were to take this angle here, this ray here, and I were to rotate it consistently around and around and around and around, sort of like the hand on a clock. That's the same exact thing that happens here. So if we started here at the initial ray at the 0 degree marker, and we went around one time, we went around an angle of 2 pi radians. And then if we went around another time, that means the angle that exists would be 4 pi. So our ray would overlap our initial ray, our final ray, our terminal ray would overlap our initial ray. And it would have a degree of 4 pi, or 360 degrees times 2, which would give you 720 degrees. So just keep in mind that these rays can revolve around the axes more than once. So for example, we might see an example like such. We might have an example where our angle starts off is measured at the 0 degree marker, which is the positive x-axis, and it goes around once, and then it goes around again, and then all of a sudden it ends right here. And our terminal ray, let me redraw that. Our terminal ray looks something like that. And I might say that this angle is 9 pi's over 4. It's 9 pi's over 4. You're like, wow, that's a big angle. And you could actually determine that by taking the idea that a pi is equal to 360. The pi is equal to 180 multiplied times 9 and divided by 4. Or I like to think to myself that, okay, you know what, if I have 2 pi is really going to be 8 pi's all divided by 4. And the key here is getting the same denominator, because when you have same denominators, you can subtract their numerators. So 2 pi is really 8 pi's over 4. 8 divided by 4 gives you 2. So now I recognize that one revolution, and this will be one revolution. So if I want to subtract off this portion right here, let me go ahead and do it in blue. Maybe blue will show up a little bit better. Oop, that doesn't look very good. If I want to subtract off, let me do it in another pen maybe. I'll do it in white. Where's my white? So if I want to subtract off this portion, so I'm overlapping it in white so you can see a little bit easier. This right here in white is 2 pi. That's 2 pi. Also the same as me saying 8 pi over 4. So if I want to find this portion right here, this angle created between the x-axis and my terminal ray, I could take 9 pi's over 4 and subtract off 8 pi's over 4, and that would give me pi over 4. And I like working with pi's over 4 because I always recognize that pi over 4 is equal to 45 degrees. So it's equal to 45 degrees. So if we want to convert this to degrees, we know that the 2 pi, we'd have 2 pi plus pi over 4, and that's equal to 360 plus 45 degrees. That's a 45 degrees. So all we do is add those two, and this is degrees too. This is degrees as well. 360 degrees plus 45 degrees gives you 405 degrees. So this angle is actually a 405 degree angle that rotates once about well, I don't want to say unit circle, but I will say unit circle at this point. Once in the first, second, third, and fourth quadrant, and then it goes pi over 4. It extends another angle of pi over 4. So to keep that in mind as you press through your problems and you try to distinguish them consistently, that it will help dramatically to convert that to something that you know. And I often will like to work with pi's over 4 much more than I want to work with 9 pi's over 4. But again, it just shows you that it rotated around the graph once, the entire first, second, third, and fourth quadrant once. So now I'm actually want to get into the basic 6 trig functions that we're going to talk about in this course. And some of you may have heard growing up, you may have heard of this little SOHCAHTOA, I wrote it backwards. So, okay, I don't even like that one. SOHCAHTOA. No, actually, I don't even know how to spell SOHCAHTOA. I think about it now. I remember the acronym. Tom's old aunt sat on her coffin and howled. So that's what I remember. Tom's old aunt. So I'll write Tom's old aunt, A-U-N-T, sat on her coffin and howled. SOHCAHTOA, I think SOHCOHTOA, there we go. SOHCAHTOA. So you get the same exact thing here. Notice the TOA is found here. TOA is the same there. The SOH is found here. And SOHCAHTOA, so it's SOHCAHTOA. See, I don't like that one very much. I spelled it incorrectly. So SOHCAHTOA. So SOHCAHTOA. I will do better next time. So that's the way that you can relate all these trig functions to what they mean. So let's go ahead and define them. So let's go ahead and define our 6 trig functions, and I will do so in white. So the first one we have is the sine, and it's actually spelled S-I-N-E, and we abbreviate sine as such, S-I-N. We have our second trig function, which is cosine, and we abbreviate cosine by COS. And our third one is tangent. And this is abbreviated by TAN. So these three, the first, second, and third trig functions, I'm going to write them in such an order because they have a very unique relationship. So specifically towards a triangle, that has an angle theta. So we're just going to assume that the angle that exists, let me write that theta a little bit better. The angle theta that exists here will create that will exist between these two rays will create a triangle, and each one of these legs will be in relation to this angle. So notice here the leg that is opposite of the angle we will call the opposite leg. The leg that is opposite, OPP. I'm going to abbreviate that with OPP. And the leg that is touching or adjacent to the angle, we're going to call that leg adjacent. And the longest leg is always known as the hypotenuse. I hope I spelled that correctly. Hypotenuse, yeah, hypotenuse. Oh, N-U-S-E, it's not N-U-S-E. N-U-S-E, here we go. I think I went for some sort of French dialect there. Hypotenuse, there we go. So the sine, cosine, and tangent relate the angle theta to all these other legs of the triangle. So I'm going to say the sine of theta. So if I think, okay, sine of theta, sine is opposite over hypotenuse. So just like that Tom's old aunt sat on her coffin and howled, sine is going to be the opposite leg divided by the hypotenuse. Cosine, if I scroll back up here, cosine is going to be the adjacent leg divided by the hypotenuse. So it's the length of the adjacent leg divided by that of the hypotenuse. So I'm going to say cosine of theta is equal to the adjacent leg divided by the hypotenuse. And then we'll say the tangent of theta is equal to the opposite leg divided by the adjacent. So we're going to say this is the opposite leg divided by the adjacent leg. And it's all a way to relate the legs of this triangle that's created by the angle. Sorry, it's the lengths of the triangle that is related by the angle and their length specifically. And this will be consistent. This will be consistent in this circumstance. And it works out relatively very, very nicely. And we can also relate three other trig functions to this same triangle. We can also relate three other trig functions to this triangle. And we're going to call this one, the first one, we're going to call this the cosecant we'll call this the cosecant, and we abbreviate that CSC. We're going to have the secant, and we're going to abbreviate that SEC, and we're going to have the cotangent, and we're going to abbreviate that COT. And the nice thing, the reason why I did it such a way is the cosecant and the sine are actually inverse functions. They're actually inverse functions. So I'll talk about the relationship in a second, but we can say the cosecant of theta will be equal to the inverse of these two. So it's actually going to be the hypotenuse over the opposite leg. The same exact relationship goes between secant and cosine, is that the secant of theta is going to be the reciprocal of these two values, so we're going to call that the hypotenuse over the adjacent. And we can also see a similar relationship between cotangent and tangent of theta, and this will actually be the adjacent leg divided by the opposite leg. So each one of those have a very similar relationship, and that's why I wrote them as such. And we are going to see that in these triangles that are created. So good luck with your trig review, and we will see you next time.